Okay, so yeah, so I want to define random walk entropy. Okay, so we did all of these things. So let's give the definition. Random walk entropy. So U, and again, the actual assumption is just finite entropy. I don't care. Symmetric adapted I like, but the actual, well, this is the actual assumption. So in fact, for this definition, I don't need anything except for a finite entropy. I mean, it could generate a smaller subgroup. It could not be symmetric. I don't care. Then how do we define the random walk entropy? Symboled by little h g u, and this is going to be just the limit as t goes to infinity of the entropy at time t divided by t. So this is the growth rate of the entropy. Now you can always immediately see that when the entropy is finite, let's say a few things. Okay? Just because this is a product of independent things. So h of xt is, of course, always less than or equal to, you give me all the steps, right? Because this is a function of these things. Now it's not a bijection. Now it's really increasing the entropy, right? More information about these are cancellations, right? Okay, but these are independent. So these are independent then of the same thing. So this is just t times the entropy of one of them, which is h of mu. Right? So when I divide by t, you see this is always bounded. So first of all, random walk entropy always less than or equal to just the entropy of one step.
Like limits or something like that.
No, limit. Oh, how do I know the limit exists? That was the next remark. The next remark was what we were talking about in the break, subadditivity. Okay? So exercise Beckett's lemma. If Vt is a sequence of real numbers, they're subadditive in the sense that at plus s is less than or equal to at plus 8s for every t and s integers. Okay? Then the limit of at divided by t exists and is equal to the infimum.
So it uses Euclidean division, right? When we measure the proof, I think.
What does it use?
It uses the division with the remainder, right?
Oh, there are many proofs of this.
If you get
Fekete, by the way, was
it's an exercise in into one, but
Yeah.
for a very strong student.
challenging.
well, you should be able to do it now.
Yeah, man.
It's good to remind yourself of how to prove this this exercise. But it's just subadditivity. I mean, it's kind of if you want. Convince yourself also, so maybe I have to remark here also, this is immediate. If the sequence at minus 1 is decreasing, if this different sequence is decreasing, that doesn't always happen. But if it is decreasing, then at minus 1 actually converges to the same limit.
I think it's the storage channel.
What?
It is storage channel.
This?
If-
It has a name, you mean? No, but it just follows from this.
This is like you can do it with the geometric mean and arithmetic mean.
No, but if this is increasing, then it's subadditive, then if it's subadditive, then it converges,
No,
and then so the Cesaro mean converges to the same limit. That's what this
Yeah,
is.
that's
I'm giving you the answer. So the trick is to prove Fekite's lemma under the weaker assumption that you just have a subadditive sequence. Fekite was in the Hebrew University, by the way. I think he was rector of the Hebrew University. Okay, so this is here's a hard exercise. Maybe you don't know enough to. Okay, maybe we do it in the future. I want to show you the time. Okay, hard exercise, not expecting you to necessarily solve it, but maybe if you want to think about it. Just so that you know about the phenomena. So what does this tell you? When the entropy is finite, you always have finite random walk entropy, right? Okay. Now, we know that the entropy is finite. A sufficient condition for the entropy to be finite is mu is symmetric adapted 1, right? It has one first moment. So sufficient condition for this is that mu is SAG1. Okay, that's easy. Okay, but the hard exercise is for every epsilon, there exists we'll find a group G such that for every epsilon, there exists mu symmetric adapted G1 minus epsilon. So you can get as close to first moment as you want, such that Hg mu is infinite. Necessarily will not have finite entropy. And the mu itself will not have finite entropy. But not only that, the random walk entropy is.
Is it a known group?
Sorry, for it's not what I wanted. Yeah, it's another group. It's I think you could do it with C. The usual stuff. But you have to be careful on how you analyze the probabilities. Maybe it's easier with some other group. Okay, this is just to show you that I really need first moment when I start talking about random walk integers. Okay, I have to be careful if I don't talk about them. So, I mean, it's a hard exercise. Which group? You want me to tell you which group it is? I mean, there may, of course, millions of examples, but no.
SN2.
I chose the free group.
Ariel, didn't you say that logarithmic moment is enough for finite
So obviously, what I said was wrong. Yeah. So first moment is enough for finite entropy, but not enough. Yeah. Think of it. If you have exponential growth, it's not enough. Logarithmic entropy is enough in a small group, not if you have a big group. If you have many elements that you need, suppose you're uniform or exponentially many elements, then you need first moment on this Suppose you're uniform on the sphere of radius r, and the sphere of radius r is grows. I'm giving you the answer, I think. The sphere of radius r grows exponentially. Okay, for example, in the free group. Okay, so you can have a measure which chooses uniformly the sphere of radius r with some probability for r. Now, if this r doesn't have a, if the distribution of the how you choose the random r doesn't have a first moment, right, which is the moment actually of mu, because that's how far you go, right?
But what
then-
does it mean?
Then if you don't have a first moment, then you can think of it, you're choosing, you need r bits with on average, right? So when you take the average, you get infinity. That's it. I just proved. I just gave you the assumption.
I just mean the definition of kth moment is that the sum of mu x times x to the power of k. Oh, so in entropy you do log of mu of x, not log of the distance.
Yeah,
That's the
Yeah, that's the difference. Just think of it. If you're uniformly distributed on something, then their entropy is log of the size of that thing. You can get the radius from this by just splitting into the difference. So actually, yeah, that's why I thought it was z, because just that's where the moment comes from. But you can put many things in the same distance so that you get more bits. You need more entropy, and that's why it explodes. Okay, that's basically the answer. Maybe it's not as hard as I thought. Okay, so now I want you to remember we had the following we had before. We defined when we have a random walk, we defined the natural filtration, and we also find the tail thing, right? So we had sigma n was everything starting from time n up to time infinity, right? So these decrease, right? They become smaller and smaller, right? As sigma algebras, because you have less things. So they decrease, and they decrease to sigma infinity, which is always the intersection of all the sigma n's. And we give this a name. So we just define this. I use a t to denote this. It's a big T. And why do I use a t? Because this is called, t is called the tail sigma algebra. Okay? And you can think of, the way to think about tail sigma algebras is you think of events which do not depend on finitely many times. So even if you cover up any finitely many times and they don't let me see them, I can still determine if the event happened or not. For example, the event that I visit a certain place infinitely many times, right? By covering up finitely many times, you can't take away the information if I visit infinitely many times, right? Or not. Okay? Which means, of course, the event that I visited finitely many times is also covered, right? But this is sigma algebra of events that don't depend on finite information in terms of time, finite in terms of time. And I'm mentioning this. So this is a theorem which was known. See, it's also very easy. It is true that the easy proof kind of appears in Kamenovich-Vaschik, but it was known before. At least this theorem was known before. So let's write a few names. Theorem. So Kamenovich-Vaschik. Now I can't even write the year because there's a debate about what year it is. 79, 81, 84. Depending if you speak Russian, don't speak Russian, if you were beyond the Iron Curtain, if you're not beyond the Iron Curtain, if you believe what they claim, if you don't believe what they claim, you get different years. Definitely appeared by 84 in the Annals of Probability. Okay, but then we also had people who did something before, and maybe Avez, you should be reading here, maybe also Delianik. Maybe also Delianik. There are other names here. Blackwell even maybe. I did some historical research, and I'm not even sure. Kamenovich says that I got it wrong. So. There's debates about who takes credit for what. But anyway, we're more interested about the the content, and this is hg nu is 0. Again, so let's think about mu with exponential moments. We don't really care, but finite moment. Okay, so mu is in SAG1. This is going to be true. In fact, we don't need symmetric even for this. We don't even need symmetric for this. You just need finite entropy. You just need finite entropy. So definitely first moment is sufficient. Then H, so the random walk entropy is 0 if and only if and only if the sigma algebra T is, I was going to write this trivial, but for us, the trivial sigma algebra is just the empty set and the all of omega. So let's expand our horizons. So if and only if, for every x in G, if I measure with respect to px, px is the probability starting from x, and I measure an event A inside the sigma algebra, I get a trivial result, meaning it's either 0 or 1, and this is for every event A in the tail sigma algebra. So there's no real information in the tail sigma. Events that are tail events, so events that happen with probability, events that don't depend on finite information, are just happen with probability 0 or 1. So for example, you ask, did you visit some set infinitely many times? That's 0 or 1. Did you do something kind of at time infinity? That's has probability 0 or 1. Either you did it or you didn't. Of course, you don't have to always have 0 or 1 because have something in stone.
It's what I remember you called it, I don't know if it's still in your book, but you called it the invariant sigma algebra?
No, this is not the invariant sigma algebra. This is the tail sigma algebra. Two different things, and they don't identify in groups. They identify, but that's identify up to measure 0. So you have to be careful. So this type of triviality of the tail sigma algebra is equivalent on a group to the triviality, this type of triviality of the invariant sigma algebra, but they are in general different things. Every invariant event is a tail event, not every tail event is an invariant. Okay? So for example,
even if the entropy is 0.
Visiting the.
For example, never visiting the origin at even times is a tail event, which is not an invariant. But they're of course equivalent up to measure 0.
Never visiting? What?
Never returning to the origin at even times. Does not depend on sorry. What I said is wrong. That does depend on finite information. Eventually not returning to the origin. Okay? Eventually not being at the origin at even times. So only at even times is a tail event. Corresponding invariant event was just eventually not being at the origin. That's an invariant. We didn't even say what invariant sigma algebra is, and maybe we'll talk about it if we get to talk about bounded harmonic functions. So KL has to do with entropy. And invariant has to do with bounded harmonic functions. Then if you relate the two, then you get something that closes this. So so let's prove this theorem. Okay. Yeah. So first of all, I didn't mention before why when Gal asked you why does the entropy converge? So I told you about subadditivity, and then I didn't say why does it prove that it converges. It converges, right? Because if you do h of xn plus t, well, what is this? This is less than or equal to the entropy xn, and then the entropy xn plus t, right? I just give you more information,
And these are independent.
right? And these are independent, so it becomes the sum. And the second one is just t steps of a random walk, so it's just x. Okay, so this is sub-additive. Okay, that's one thing. Second thing, so this is why it converges, right? When you divide by two. Second thing is, well, if you're a bit more careful about these things, then you can look at xn plus 1 minus h of xn. Okay? Now I'm giving the stronger condition. You're going to see that this decreases. Okay? So what is this? Well, the entropy of xn, I can also write as the entropy of xn plus 1, I mean, just same number, conditioned on x1. This we already proved, right? If you condition on x1, right, then this looks like an n-step random walk instead of an n plus 1 step random walk, right? Has the same entropy because you can go between x1 to the minus 1 multiplying this or not, right? The same entropy. And here I'm using this group translation property. Okay. Well, this difference we can actually now start writing out. What is conditional entropy? It's joint entropy minus, becomes a plus, what you conditioned on. Right? But look at this term. This term is completely symmetric in the two variables, xn plus 1 and x1. Right? Because it's the adding the two, but incidentally, this is known as the information, the mutual information. And the fact that mutual information is symmetric is a very important, simple but fundamental thing. So this is the information between xn plus 1 and x1, and this is information is, this is definition, what information between two variables is. Information is symmetric. You could just see it because this plus this minus the mutual, the joint entropy is symmetric. I mean, it doesn't care. Okay, so I can go back instead of conditioning on the x1. So you see, this is equality. So information is also equal to this. But I could have reversed the roles of xn plus. See, from this you don't immediately see that it's symmetric in xn plus 1 and x. This difference is symmetric, and so you get x1 minus x1 conditioned on xn plus 1. But wait a second, what is this guy? This guy is exactly, if I condition on the future, then I can condition on the whole future, right? So this is equal to x1 minus x1 conditioned on sigma n plus 1. Right? This is what we said. If you condition on the future, if you know future, then you just can put in all the future. Okay? Now what happens when n goes to, so first of all, what happens when I increase n? Make n bigger, this guy becomes smaller, right? Entropy becomes bigger, minus becomes smaller, right? So when n goes up, everything becomes smaller. So this is a decrease. Where is it decreasing to?
To hx. The entropy.
To take n to infinity, and we know just plug the infinity in there, right? So it's decreasing to this. Which if you want, you can think about, this is the information the tail has on x1. So the information, at what happens at infinity, how much information is it giving you on x1? Now, I cannot reverse the roles here because now I have schema algebra and things, so there's no way to reverse it. But you should think about, this is the information. This is the information between x1 and the tail. Okay? So this is kind of telling you, x1 is going to, I'm going to remember x1 up to time infinity, right? Now, another thing is that when this term is decreasing, what does it converge to? It has to converge to the same limit as the hxn over n, right? So this also converges to, let me put it here. So this also converges to decreases to what? To the infimum of hxn over n, which is the limit of hxn over n. This is just a general fact about subadditive sequences, okay? Which is random walk entry. Okay. Now, one more thing. Is that you could also have done this by replacing in everything I did.
Instead of n plus 1, n plus k.
Well, not n plus k, but yeah. Okay. So one more thing is that just to get the complete theorem, I don't need it. Anyway, I'm just giving you this. This whole thing was just for general knowledge, and maybe if we get back to bounded harmonic functions, we'll say something. One more thing is that we could have looked at h of x1 up to xk. The information I have on the first k steps of the random walk with the theorem. We could have looked at the same thing. So that phenomenon maybe motivates looking at this. Okay, what is this? Well, this is equal to the limit as n goes to infinity of, instead of conditioning on the tail, I can just condition on the future. When n goes to infinity, I can just take n large enough, right? Because the tail is the limit of the sigma n's. The sigma n's is the same as conditioning on the future. So I have the h of x1 xk minus h of x1 up to xk. I should think of x1 up to xk as one thing, just taking values in some more complicated space, but it's one thing. And here it's conditioned on xn. Right? This is taking n to infinity, I can put an n there, right? So for large enough n is in the future, and I can do this. But remember we said that information is symmetric, so I can reverse the roles of these two things. So I can get that this is equal to the limit of h of xn minus h of xn conditioned on x1 up to xk. But what is this? This is just a walk for large enough n. This is just looking at the first k steps. It doesn't care. It just knows how do I get from k to n, right? Okay. So what I have here is that this becomes the limit as n goes to infinity of h of xn minus h of xn minus k. And what do I do with this? Well, I just telescope. So this is the same as the limit. N goes to infinity. And I can go from 0 to n minus 1 of h of xn minus j minus xn. Let's do from xn minus j minus 1. Not up to n, but rather up to k. Well, this is telescopic sum, right? So you're only left with the first and last terms.
No, but the last term is not xn. If you want n minus.
No, so
k.
start 0.
Okay.
This is n
Oh,
minus
yes.
n minus 1, right? Then
And
it's
the other.
plus n minus 1 minus n minus 2 plus n minus 2 minus n minus, and the last one is n minus k minus 1 minus 1. So, okay? It's n minus k. So this is exactly the same thing. But these guys differ by 1. These guys differ by 1. There are finitely many guys in the sun. I can bring the limit inside. The limit of each one of these, we already know what it is. And there are k of them. They all have the same limit. I mean, right?
K times the h
Right?
of 1 minus.
Each, for fixed j, each one of these has just the limit, which is the random walk entry. So this is just k times h g mu. Okay, so this is what I wanted. It's a more general phenomenon. Okay? This is equal to this. Okay, so let's see both directions. one direction, right? We're proving something about Fermi bands. So one direction is that
We're proving the theorem?
yeah, proving that this is a proof of the theorem. Okay, proof of so one direction is if the tail sigma algebra was trivial, well then it okay. So if whatever, in fact it's enough to say this. 0, 1 for every a in T, right?
Not dependent on X?
No, just for fixed x equals 1. When I don't write x, I mean x equals 1, right?
Okay.
Then what happens to this distribution? This we already said. Okay, so then x1 is independent of T. This is just true because T is trivial. I mean, if every event has 0 probability 0, 1, then anything is independent. Okay? The next one is independent of T. So by the k equals 1 case here, okay? The k equals 1 case, what we get is that h g mu is 0. Okay, that's one
The
direction.
entropy of X1 given T is just the entropy of X1.
Yeah, it's independent. Or if you want the mutual information is 0. Yes. Well, yeah, because we said that when x1 is independent of a sigma algebra, then the entropy, conditional entropy is just the original. Okay. The other direction is assume for the other direction that the entropy is 0. Then by the k case, for general k case, right? Then x1 up to then let's write this thing. F t, right? So everything generated by x1 up to xk, right? So the conditional entropy stays the same. So we said that means that they're independent. This is independent of that, right?
Did we show the other direction? I mean, we showed one direction.
We didn't show the other direction?
Didn't we? I don't recall. What? Only if, even only if?
Yeah, it is.
The entropy
We
is
wrote
zero,
it
then
as a
it is
different.
independent.
We wrote it additionally, yeah.
We wrote it, but we didn't prove it.
as
Last time.
That's proof the other direction?
It was an exercise.
Oh, okay.
I don't think we did it.
Okay.
Yeah, I mean, but it's true. It's true. It comes from the, in a sense, from the equality condition in Jensen. You have equality, right? So it means something has to be constant. So okay, so ft. But anyway, it's true. Okay, it's true. Okay, random variable conditional entropy is 0 if and only if the variable we're questioning is independent of the sigma algebra. Okay, so this means that anything generated by those random variables, so k equals t, would say that ft is independent of the tail sigma algebra. What? For every t, right? Fix a t, take k equals t, the difference is 0, so ft is independent. Okay? The fact that t is trivial is now called the Kolmogorov of 0, 1. This is exactly what Kolmogorov said. If you have a sequence of random variables, okay, and you define the corresponding ft, and ft is independent of the tail for every t, then you get that the tail events all have probability 0 or 1. But let's prove it. Let's prove it. Okay. So how does this lead to the fact this is called the Kolmogorov? So finish it by Kolmogorov, just so that you know what this is called. 0-1 law. Okay, there's an ancient thing from classic times in probability, but how do you prove it? So Kolmogorov is 0-1 law is exactly stating what I want, right? Okay, so so what do I prove? I want to show you how you prove Kolmogorov-Zermelo. So the assumption is that you have this FT is independent of the tail, right? The tail and the FT are defined by the same sequence of random variables. Now, that's the only thing I'm going to use. Okay, so we take an event, so let A be in the tail. Okay, what we're going to show is that A is independent of itself. Right? So how do we show that A is independent of itself? Well, so yeah, sorry. So first of all, sorry. Let's take A.
Because the FT like exhausts the.
Oh, well, it's not because of exhaust. It's because everything is cylinder sets. So
The limit of cylinder sets?
Yeah, because you can
approximate anything by cylinder sets, right? So if I take an event, if I take a tail event, right, then I can find then fix epsilon, and we can find a epsilon such that the symmetric difference between a epsilon and A, so A epsilon
Cylinder.
cylinder, such that the probability that A epsilon, the symmetric difference, is smaller than epsilon. So you find an epsilon approximation of this thing. You need to prove that this can always be done, but you can always do this in this because everything comes from the cylinder sigma algebra. That's what it's.
You can prove this is a sigma algebra, right? All the sets satisfying. So then for every epsilon, you have such a set.
That's an interesting thing. Yeah. Then you have to show it's the whole cylinder. Well, cylinder sigma algebra is basically it kind of gives you this happens. So you prove this, okay? And then since I have an epsilon approximation, now all I have to do is so now I compute the probability. Okay, so A epsilon is a cylinder set, so it means it belongs to some FT. That's what it means, right? So there exists some T such that A epsilon, T epsilon, right? Such that A epsilon is in FT. So T depends on epsilon. And now A epsilon what did I want to do?
Now we want to condition.
I want to show that A is independent of itself, right? Yeah. So probability of A, right? So this is equal to the probability of A intersection A epsilon, okay, plus the symmetric difference, right? Which is everything less than or equal to.
Yes.
Okay. Plus so what I should write here is actually the difference between these two things in absolute value is less than epsilon. This is the approximation I should have been using, but it follows from that. Okay. And it means less than this plus the symmetric difference, and it's more than this minus the symmetric difference. Okay, and once you have that, then what is this? This, because this is tail independent of FT, this is the product. Okay? So this becomes P of A times 1 minus P of A epsilon. This is less than epsilon, right? And now you want to say that P of A epsilon is very close to P of A with another loss of maybe some epsilon. Okay? Because A epsilon is a good approximation for A.
We have 8 times. Oh,
What?
no.
Yeah, so this tells you that yeah, so this should be greater or equal than P of A.
Can we write A as limit of set in the FT? As limit of cylinder sets?
What?
Can we write A as limit of cylinder sets in some sense?
Yeah, I mean, this is what's written here. But this also gives you that 1 minus PA epsilon. So this is bigger than 1 minus PA minus epsilon. The most you can lose is epsilon, right? And the difference. Okay? So this side is bigger than this side. This could have already been negative, right? But for small enough epsilon, it's not negative, plus this 1. And then you get this is less than epsilon. Epsilon. And you could see that taking epsilon out to 0, now there's no A epsilon. So now you can take epsilon to 0. Taking epsilon to 0 shows you that P of A times 1 minus P of A is 0. Okay. All you need is, what do you need? What did I actually use? Yeah, I used it. Well, yeah, I basically used this. That's right. Okay.
Okay.
So this is how you prove. Basically, in a cylinder sigma algebra, this is what Kolmogorov said. Take cylinder sigma algebra, and you have if the tail events are independent of the filtration, of the natural filtration, then they all have 0-1 probabilities because they're all independent of themselves. Sense. Okay. This is the second part of the Kaimanov general logic, or the entropic criterion, right? Because we proved if the entropy is 0, then everything in the tail is 0. Okay. Next time we'll see how to quantify at least one direction. You cannot quantify the other direction of this identity. Well, not exactly this one. Something.
Thank you.